So, friends, welcome to this lecture series of geomorphology, and today we will continue with the fluvial processes. So, in the last class, if you remember, we are emphasizing on this longitudinal river profile, and finally we concluded that the longitudinal river profile should be ideally concave upward. But within that concavity, there are certain points, they are called nick points or king points, which show the local convexity, and those nick points or these locally convex points are of geomorphologically immense importance, because these are these regions which produce more sediment, these are the regions which trap sediments, and these are the regions to study tectonics or fault movement or any basement or any hard rock protrusions like those. So, that longitudinal river profile of a channel that does not remain at the same level throughout its lifetime. So, due to local base level fluctuation, the longitudinal river profile also shifts. So, this was the summary of this last class. So, today and in this class we are going to discuss about how this grain size, either it is a coarse grain or it is a fine grain or is a dissolved sediment, how they define the channel shape, and the channel habit, how is it influenced by this grain transportation and slope and the amount of sediment that a river is transporting, and the stream competency. Channel shape and solid load. Solid load, we have different types of loads, as we know. One is suspended load, that is always in the suspended condition. So, they are mostly the fine grained clay size particles. Then saltation, saltation means fine sand itself. So, it will move like jumping, that is saltation, and coarse grain sand, pebbles, cobbles, boulder, they are transported by rolling on this river bed, they are called tractions, and some of this sediment they are transported with a dissolved condition, they are called dissolved mode, that is not of important in terms of fluvial geomorphology is concerned. So, here once we say it is a solid load, that means these former three types of sediments, that is traction, saltation and suspension, these three types of sediment we will deal with, and we will see how the proportionate change of this sediment, then how they influence the channel habits. And second thing, that during this transportation of the sediments, they always in interaction with the bed and bank. Sediment, sometimes it is suppose a river is transporting some sediment, and either it is any type of mode, any type of this three mode, and this river, this competency decreases, that means river water decreases, velocity decreases, so it will remain there. So, during next high energy condition of this river, suppose during flooding time, that sediment will transport to other place or the further downstream, and the same place will be occupied by the other sediment. So, this way a sediment is transported from this origin of this river to this mouth of river, and some of these sediments they reach to this deep sea level, and maximum of the sediment of a river they are distributed and remain within that flood plains. But whether this channel will be deep enough or channel will be shallow enough, it will be wide channel or it is a narrow channel, it is a meandering channel or straight channel or it is a braided channel, all those depends upon what is the sediment particle size, how much amount of sediment is there, what is the dominant sediment type a river is transporting in a particular reach. So, that reach will take that shape depends upon the sediment particle size. So, stream competency defines the composition of bed and bank of this river. Stream competency, there are two terminologies, one is stream capacity, another is stream competency. Stream capacity, it is the total amount of sediment a river can transport at a particular time. So, it is stream capacity, and stream competency, it is the largest size a stream can transport, largest size of grain or largest size of a crust a stream can transport. This is stream competency. So, stream competency defines the composition of the bed and bank of the river. Either this bed will be rough, the bed will be smooth, the bank will be a narrow bank, or it is a wider bank, it is a shallow bank, like that. So, although there is a smooth or is a rough surface, that depends upon the stream competency. And throughout this lifespan of a river, if you take a time window of hundreds of years or so, this channel shape that does not remain same. For example, if you see here, this is a figure which is taken from Bloom. Now, you see this is the channel shape in a particular time, and the same channel is like this with another time, again it is with same time, again another time. So, that means I want to say with time the shape of this channel, the cross sectional area of a channel, it changes. That depends upon this amount of sediment, that depends upon the erosional capacity, depositional capacity, and through which the bedrock through which the river is transporting, climatic conditions, tectonic scenario, all those factors that defines what should be the channel shape. So, in a particular space with a different time, the channel shape can vary. Okay. So, a constant exchange between the bed and bank with load takes place during transportation. So, there will be some sediment, there will be interact with the bed, some of the sediment they will interact with the river bank, and there will be constant exchange between this sediment and water, bed and bank, and this load that always takes place during transportation. And channel roughness, it is determined by the grain size or bed forms of this alluvial bed. So, channel roughness, how rough the channel will be or smooth the channel will be. Either it is symmetrical, channel cross section will be symmetrical, or it is asymmetrical. So, all that depends upon the grain size or the bed forms of the alluvial bed. And roughness affects turbulence. Now, if it is a rough channel through which the river is transporting, so river will always in a turbulent mode. So, turbulent mode means now the competency increases, and this complex adjustment between discharge, grain size of this load and channel shape, velocity and amount of load is constantly in progress. So, that means all those factors, grain size of this load, then channel shape, velocity, amount of load, all those factors that will be changed with this roughness, channel roughness, and that means these are the dependent variables. So, if channel is smooth, this will change, or if coarse grain is, suppose a river is transporting only the coarser part, so this channel will be rough. So, that is rough channel, again that will increase the turbulence, increase the competency. So, that means one factor is changed, so it will affect the another factors. So, how much water is discharged in a cross section? In the last class we were talking about the gauging stations. There are many stations, gauging stations throughout this river course, and constantly we are monitoring with a different time interval how much water is passing through, how much sediment is passing through, what is the velocity of this river, and how much sediment in traction mode, how much suspended mode, saltation mode there in a particular time in a particular gauging stations. So, this totally and entirely it is keeping this track of this discharge of sediment, discharge of water. So, water discharge of a particular segment of a river at a particular point, that is Q, it determines the size or cross section area of a alluvial channel, but the amount of and grain size of this sediment load determine both the channel cross section shape, width depth ratio and habit. So, what should be the width and depth ratio? What should be the channel habit? Channel habit, that means if it is a meandering channel, it is a straight channel, it is a braided channel, or they are called the channel habits. So, what should be the cross sectional area? How, if you look a cross section, how it will look? It is a narrow channel, it is a symmetrical channel, it is a asymmetrical channel, it is a wide channel. So, how it will look, and how this channel, if you looking from the top, how it will look. For example, if you see here these figures, this is meandering channel, this is straight channels. So, the straight channel will be like this, meandering channel is there, sinus channel is there, braided channel is there. So, that means in a cross sectional look how it will look, similarly in a aerial look how it will look, that all depends upon this discharge and grain size, amount of sediment, all those factors defines what should be the overall look of a channel. So, if you see here, it is some of these points has been described here in terms of this figure. Suppose we are taking sediment load as a factor. So, once you are coming from towards the straight or the straight channel and it is a braided channel. So, here more suspended load, this side is more bed load. Similarly, this side is more finer grained, this is coarse grained sediments. Then increasing stability, it is decreasing stability, that means bank stability is concerned. Similarly, sediment grain size is concerned. Similarly, discharge variability, if we see low variability discharge, it is monotonous discharge, but here high variability discharge. Then channel slope, it is lower slope, it is higher slope. So, that means those factors here, that means if it is finer size and this side is coarser size. So, if you are increasing slope, decreasing slope, increasing suspended load, decreasing suspended load, all those factors that define how a channel will take its shape, what should be the channel habit. Because channel shape varies so much, you see, as we have discussed here, somewhere it is a sinus channel, somewhere is a meandering channel, somewhere it is a straight channel. So, there are number of variations are there. So, if we take this channel banks, if we take this trace of the channel bank, we will find different variables. So, it will confuse the system, it will hinder our calculations. So, in that case what we generally to define the channel shape, whether this channel is straight, this channel is sinus, it is a braided or it is a anastomosis channel, like that. We take the help of this Thalweg. Thalweg means it is the line connecting the points of maximum water depth in a general downstream direction along this channel when describes channel habit. So, how a channel habit will be, either it is straight channel, channel habit it is straight, or it is straight channel, or it is a meandering channel, or it is a sinus channel. So, all that can be defined through the Thalweg, through this shape of this Thalweg. So, Thalweg is the line which is joining the highest water depth of a channel in different points. For example, if you see here, this line, this dotted line is defined the Thalweg. So, this Thalweg means it is representing this highest water depth. Here is suppose for example, this is the point here, higher depth, higher, this is the cross section we are talking about, this highest water depth will be here. This is the cross section we are taking, the highest depth water depth will be here. In this cross section here, higher water depth will be here. So, once we are joining those points, so it will taking the shape. So, we will define either it is a straight channel or it is a meandering channel. In the meandering channel, you see here this channel, the Thalweg, it is moving like this. In a straight channel, this is moving like this. So, that means this channel shape will be defined by the Thalweg of a river, the line joining maximum points, maximum depth. So, most of this Thalweg is passing through successive pools and ripples. What are the pools and ripples? For example, if in a channel is this channel, if you talk, we are talking about. So, here is this violet line is defining the Thalweg. Within that Thalweg, within this channel, some part of this channel, it is deeper part and they contain water throughout this year. And in between, if you see here, we are getting water here, but in between here where we have sediments. So, the sediments, they are called ripples and this is called pools. So, that means a Thalweg is passing through pools and ripples, and we know ripples, that means it is somewhat elevated part because sediment is deposited there. Pools, they are the deeper part, somewhat lower elevation, comparatively lower elevations is there. So, that a Thalweg is passing on upward and downward. If you see this cross section height elevation of a Thalweg in downstream, the Thalweg is not in a straight line, it will move up and down, though overall it is moving downstream, but within that we will get this type of structures. So, that means Thalweg it defines the channel habit. So, that means here we have succession of pools and refills. These are the refills, that means those parts which are filled with sediment, these are called refills, and those part which contains water, that is called pools, which might be sedimentary bed forms or bedrock ledges. So, this refills not necessary to be always to be sedimentary deposits, it may be bedrock, that means rock exposure should be there. So, that means irrespective of it is either it is a sediment deposit or it is bedrock exposure. So, that means we have no water there. So, that is why it is called refill, and pools we have water there. So, the pools and refills of stream bed cause the Thalweg to have an irregular shape, rising and falling in the downstream direction, as we are discussing here. This Thalweg it is moving, rising at these refills and falling at these pools, again rising at the refills and falling in the pools. So, this rising and falling of Thalweg occurs in a cross section. Similarly, in a plan view, this movement of this or the shape of this Thalweg, the movement of this Thalweg, that defines what type of channel we are dealing with, either it is a straight channel or it is a meandering channel or it is a braided channel, like this. So, if you see here, once we are saying about this Thalweg movement, now you see this is the cross section A to A dash. Here this using refill, you will find a channel which is symmetrical shape. But if you see here at these pools, we are taking a B to B dash as a profile and we are getting an asymmetric channel. So, at pools this channel will be asymmetric, and refills this channel shape will be symmetric. And some of these rivers, they have multiple channels, not a single channel, multiple channels, and they bifurcate at some point of space and again rejoin with this main channel and after few kilometers, and they encircle or they encompasses some of these islands in between them. It is mostly the permanent islands or the stable channels are there, and permanent island with a large island separating several relatively stable channels. For example, these are called the anastomosine channel or anabranching channels. For example, here anastomosine and anabranching channel, that means you see a channel is bifurcating here and they are meeting here again. So, and these are these islands, they are separated by somewhat stable channel, these channels are stable. Okay. So, this type of channel are called anabranching channel. Single channel alluvial rivers may have reached that are straight, meandering or braided. So, that means once we say multiple Thalweg, that means we are talking about this anabranching channels, but single channels, that may be straight channel, that may be meandering channel, that may be braided channel. So, braided channel is only single channel, though there are branches there are, but these are not permanent. Here the difference between these two, this anabranching channel and this braided channel is that these are permanent and these are stable channels, but here these are not permanent and this is not stable channel, isn't it. So, that means once we are dealing with single channel, we are talking with a straight channel, we are talking about meandering channel and braided channel, but multiple channel, that means we are talking about anabranching channels. So, depending upon this Thalweg, this bifurcation, this reunion and a single Thalweg or multiple Thalweg, we have 6 channel habits or channel patterns have been defined in terms of their relative stability. Relative stability, it is important. That means one end it will be most stable channel, at the other end it is the least stable channel. Their sediment load and grain size, some of these channels they are exclusively transporting coarse grain particles, and some part of this channel or some channels they are exclusively for fine grained particles. Ratio of suspended load to bed load, that means how much suspended load is there, if suspended load is dominating or bed load is dominating, and other related variables are there. So, depending upon this, there are 6 channel habits have been identified and it is given in this figure. If you see here, if you see this axis, this side is suspended load, this side is bed load. That means those channels which this side they are bed load dominated, and those channels which are this side they are of suspended load dominated, and some of these channels they are transitions. Now, similarly, if you see here, it is braid channel pattern, it is meandering, it is straight. For example, here it is a straight channel. Straight channel, that means here if you see these are some variables are given. Relative stability. Relative stability means in straight channel it is high. That means straight channels are highly stable, and this side it is braided channel. Braided channels have relative stability is low. So, that means braided channels are low stability wise, they are lower stable or less stable as compared to straight channels. So, that means straight channel if it is there for more time, you can see its straightness is remaining there, but in braided channels always it is changing here and there. Sometimes water is flowing this side, sometimes water is flowing that side. Here river bars are there, sometimes the bar is migrated to that side. So, it is most unstable channel. Then it is, if you is coming further downward, so changes in habit tend to be abrupt when certain threshold conditions are reached or exceeded. So, whatever these parameters we have taken, sediment load, grain size, ratio of suspended to bed load ratio, all those some limit is there. For a particular channel, this should be the bed load to suspended load ratio. So, if it is extending, if it is exceeding to the threshold limit, that straight channel will converted to meandering channel. Again, if it is exceeding that limit, then that will converted to again meandering channel, and this is a transition, and finally it is coming to braided channel. So, here if you see here valley slope and channel forming discharge, and here it is increasing. So, that means discharge will be more here and it will be less here. So, sediment it is suspended load, this side will be more, bed load this side will be more. Sediment grain size, coarser grain in this side, finer grain in this side. Then flow velocity, it is high this side and low this side. Stream power, it is high this side, low this side. So, that means all those parameters that have certain limit. Within limit, for example, for straight channels, these parameters have certain limits. If that limit is exceeding or it is decreasing that limit, this channel will change to different pattern. So, first let us talk about this straight channel. Straight channel, it is a suspended load channel. That means, here in the previous figures we have discussed here, this is suspended load. It is a straight channel mostly dominated by suspended load, and low velocity with low gradient, low total load, and low velocity may be straight and narrow without migrating submerged transverse bars. Such channels are rare, but its natural may be quite stable. In nature, sensu stricto straight channel are rarely found, but if it is there, it will sustain for long time, it will remain stable, it is there. With mixed suspended and bed load, straight channel may develop alternate bars and a sinus Thalweg, although this channel banks remain straight. So, here if you see, suppose we are increasing the bed load to certain extent, though the channel habit remains straight, but we are creating some bars, and once bars are generated, the bars migrate downstream. So, due to this migration of these bars, the shape of the Thalweg changes. So, as a result, this straight channel will convert to a meandering channel. So, if you see here in the sinus Thalweg, although the channel's banks remain straight, the alternate bar migrate downstream remaining on the same side of this channel, thus exposing each bank to alternate intervals of erosion and protections. So, now here if you see, suppose this bar is generated here and this bar it is migrating in this way, and this migrating. Suppose we are talking about, suppose this is this channel and we are creating a bar here, and this is the channel we are creating a bar here. So, this is Thalweg is here, it is, and Thalweg is moving this way. So, that means here we are getting erosion, and here we are getting erosion, and here deposition and deposition, but this bar migrates. So, once it migrate, that means here the sides of erosion becomes protected, here the sides of erosion become protected, and that is why this erosional site becomes gradually protected, and this protected sites become the sites of exposure to erosion. So, that is why the channel shape, channel habit change with time. Another type of channels that is artificially created, or these natural channels, they are artificially straightened, that is called channelization. The process is called channelization. So, channelization is the artificial straightening of channel. If you see this coastal area topocits from 1990 to recent days 2017 or 2015, you will find drastic change in channel habits. So, due to this flood control program, most of these channels, natural channels, they have been artificially straightened. So, artificially straightening channel has some positive as well as some negative impact. For example, suppose there is a channel, earlier it was moving like this, and during flood the water was distributed throughout this area and it is getting inundated or flooded. Now, due to channelization we have made it straight. So, that for this particular area we have solved the system, solved these flood problems. But once we have straightened the system, now you see we have a straight channel, gradually this bank erosion takes place. So, once the bank erosion takes place, so more and more sediment is produced. So, more sediment is produced and it is transported to the straight channel. It once the straightness is decreased or the straightness ends, the sediment will be deposited there. So, that means in the downstream the sediment will be overloaded and finally it will create some, again the flood problem will be there. So, that means though artificial straightening has some advantages, that for a particular time, for a particular area we are solving these flood situations, and straightening, that means for our communication purpose we have reduced the time, we are saving these fuels like that, but it has some problems. So, that is why artificial straightening should be done judiciously with depending upon this populated area, or depending upon the area which is under active use or it is abandoned. So, artificial straightening of alluvial channel to decrease local flooding, to reclaim floodplains greatly increases bank full discharge, stream velocity and downstream dam valley gradient. The straightened reach usually deepens rapidly, followed by widening due to bank collapse. Aggradation downstream of this channelized reach may cause increased flood there. So, that means we are solving one problem and again we are creating another problem. Then the same thing is written here, how it works, extra benefit and disadvantages. So, if you see here, meanders are removed by building artificial cut throughs. This makes this water flow faster with reduced flood, because water drains downstream more quickly and does not build up to a point where the channel cannot contain it anymore. But extra benefit is there, it takes less time to navigate the river because it has been made shorter. Disadvantages, flooding may happen in downstream, instead of flooding water is carried there in faster. So, that means artificial straightening, that means we are moving water faster than it should move naturally. So, that means in downstream we are creating more floods as compared to this earlier situation. So, these are some advantage, disadvantage and how it works. So, this is all about the straight channels, channel habits, and in the next class we will talk about the remaining channel habits like this braided channel, like the meandering channel, how they works, how the sediment capacity, how the sediment characteristics that change these channel habits in the different reaches of a river. So, I think we should stop here. Thank you very much.